So welcome back. So we'll continue.
So in the literature of game theory in evolution, we don't say traits or alleles anymore because we really don't know what is that underlying genetic basis that might shape a behavior. There might be many genes, and so we only talk of behavioral strategies. So now what are pure strategies? Pure strategies are basically when everyone in the population adopts the same behavior. Okay, so in this case, what are the pure strategies? All being hawk, right? Or all being doves, right? So, or all doves. So these are two pure strategies. And now, just because, and again in the language of frequencies, it's basically corresponding to p is equal to 0 or 1. Okay, nothing really fundamentally different. Now, we want to understand the stability of these strategies. Just because a strategy exists doesn't mean it's stable. Okay, so which of them will be stable? Okay, so how do we do that? We do that via something called invasibility analysis. Before we even get there, let us compare the payoffs of pure strategies. If everybody was a hawk, what would be the payoff? What would that be? V minus C over 2. If everyone was a dove, what's that corresponding payoff? V by 2. So if you were to naively compare the payoffs of pure strategies alone, what will you conclude? So doves are the optimal strategies, okay? But optimal strategy need not be stable, okay? That was the sort of insight that John Nash had, okay? Optimal strategies are not necessarily stable strategies. So you cannot directly compare these two and conclude that therefore all doves will be a stable strategy, okay? Yes? Yeah, group or a population level, yes. Well, it sort of depends on how you do define, but yeah. So what is optimal for an individual is not necessarily optimal for a group. So you're absolutely right, and that's precisely what evolution does. Evolution cares about how relatively you are compared to everybody else. It doesn't care what's optimal for the entire population, and that's also precisely what these game theory based analysis helps us do. But a naive comparison based on, let's say, something called an optimization theory. If there was something called an optimization theory, you would conclude that this is optimal for the population, therefore everyone must be doing this, right? But that's not necessarily a stable strategy. Okay, now how do we identify stable strategy? The idea is exactly the same as the previous analysis we have done, except that we can actually give some nice terms for each of them. So what we do is, once you have identified few strategies, what you do is do something called the invasibility analysis. What does it mean is, start with a pure strategy and what happens in evolution usually, let's say if everybody was a dove, what's a likely scenario in the next generation? Some mutants will arise, right? When will this strategy be stable? When the mutants that have arisen, they don't increase in their frequency, right? That's precisely the idea behind invasibility analysis. Start with a pure strategy and compute fitness or payoff of rare mutants in this population. So if everybody was a dove, if there were a few hawks, what happens to these hawks? Will these hawks will have a higher fitness compared to the much bigger dove population? If that happens, what will you conclude? Those hawks will now increase in number over generations. Therefore, the pure strategy of all doves will not be stable. Likewise, if everybody was a hawk, if we introduce a few doves, If those doves have a higher fitness than the rest of the much bigger hawk population, doves will now take over, right? So what we do is we basically check stability of each of the few strategies that are available, that are sort of meaningful for the specified game. Okay, so shall we do this now? So let's assume that everybody is a dove, because that seems like the best thing to do ideally, right? And then let us compute the fitness or the payoffs rare hawks in sort of how do we do this? We basically compute now we have to compute the fitness of this very small number of hawks. Okay, now what will that be? Again, there's a baseline fitness. Okay, and these hawks, they're very small in number. What is the chance that these hawks will interact with another hawk? Huh? It will be solved, sorry? It will be very, very small, right? Because they're already so small. So imagine that this is an entire student population of all dove strategies, and there are just a few of us who are hawks here. And then let's imagine we're all mixed up in the entire population. Now, if you were to pair up two individuals randomly, if you were to pair one of the hawks, who is very rare, with one of you randomly, will the other guy be, what's the most likely scenario for the other guy to be? Dove, right? And the other guy being hawk is actually very, very tiny. It's so tiny we don't have to even bother about contribution from that payoff. So basically, this is approximately is equal to probability of hawk interacting with dove times the associated is that right? What would that be? Plus this is basically, since almost everybody is dove, this probability will be close to 1. And this will be, what happens to the hawk now? What's the payoff obtained by hawk? Is V. Omega 0 plus V. Okay. So basically the rare hawk has a payoff of omega 0 plus V. What's the payoff of everybody else in the population? Almost everybody else is a dove, and they all have is that right? What does this mean? This implies that rare hawks have and consequently they will invade. So this tells me that this all dove strategy is not a stable strategy. So evolution will not reach this strategy. And does this depend on the value of V and C, by the way, this analysis? Right? It's always true. It's true for all values of V and C. Which means that for this game, independent of the values of V and C, all doves is an unstable strategy. That we're not saying. It's like exactly like stability analysis, right?
At the first point, will it spread or will it not?
Exactly.
If it does, it will.
Exactly, yeah. And isn't that precisely what we did when we did stability analysis? right? We had an equilibrium, we made a small perturbation, all that we could say was, does it increase or decrease? In fact, we didn't know where it will end up. That to know that, we need to know the rest of the world, rest of the equilibrium and their stability and so on. Okay, can you all now do the stability of this pure strategy? Can you all work out the maths for this? So basically, before you start doing so, when we do the invasibility analysis, if you find that rare mutants cannot invade this pure strategy, we call that an ESS. If invasibility fails, this implies that strategy is called ESS, which stands for evolutionarily stable strategy. Can you hear me? Okay. First point I want to make is that when you compute you will first compute the payoff of the rare doves in this pure strategy, right? And then you will compute the payoff of the hawks, and you will compare them. Okay. And I think many of you are able to do this, but some of you are not paying additional attentions. So compare them not just by eyes, but just write down the full equation and write the actual condition. Okay. Okay, for example, when is this greater than this? Okay, because in this scenario you will get two possible outcomes depending on the values of V's and C, which was not the case there. Okay, so pay attention to that detail, which is extremely important. Okay. The board now. So how do we do this? You consider rare D in basically dominant hawk population, right? And then compute its fitness. So it's approximately the baseline. So what's the probability of D interacting with D? That's close to 0, right? Because I already saw it anyway. That part is 0. What's the probability of dove interacting with a hawk? Pretty high. But the associated payoff is 0. So that thing, this is just W0. So the payoff of the rare doves is just nothing but the baseline payoff. Okay, now we have to look at payoff of, hawks which are in a dominant, which are in the dominant strategy now. So there's of course a baseline. What is the probability of hawk interacting with the dove? It's again close to 0, very small, right? So you're going to ignore that. And what's the probability of hawk interacting with the hawk? That's pretty high. And in fact close to 1. And the associated payoff is V minus C by 2. Okay. So we have computed the two payoffs now. The next step is to compare them. So this is what I have introduced now. So let us see how well they are doing compared to these. So WD greater than WH, let's say less than W. If this is true, then what happens? The rare doves, the one that I introduced, will all die. Okay. So when is this true? If that is true, if this W0 is less than W0 plus V minus C over 2. Okay. So W0 cancels, and then this is true if V minus C is greater than 0 or V is greater than C. So basically the rare mutants will die, and therefore pure H will be a stable strategy. pure H is stable if V is greater than C. And that's also precisely what we found in our previous analysis, right? So pure Dow's strategy was always unstable, but as long as V is greater than C, pure Hawks will be a stable strategy. So everybody will turn into a Hawk if V is greater than C. So that's the case one. An alternate case is that WD, is this possible? I mean, the rare mutants do have a higher payoff than the dominant Hawks. Is that possible? Indeed, that's possible when this is flipped, right? True if V is less than, I mean, the resources are actually, the cost is actually more, cost of fighting is more than that of what you gain by resources. In such a case, rare D invades right. In this case, pure H is not a stable strategy. So what this also means that for this specific case, if V is less than C, neither of the pure strategies is stable. So if everybody is a Hawk, Dows will invade. If everybody is a Dow, Hawks will invade. So what's going to happen? Neither of the extremes are, if this is all Hawks, all Dows, both of them are unstable. What happens? They will probably reach some intermediate point. How do we find the intermediate point? So intermediate point means that both the strategies basically coexist at a mixed proportion, right? So basically the way to analyze this case is, look for pure strategies. Okay, if one of them is if one of the pure strategies is stable, that's where evolution will take you to. On the other hand, if neither of them are stable, you have to look for what are called mixed strategies now. Yeah. That's true for all values of V, right? That's true for all the cases. What is not true? Yeah. Therefore, it's not an ESS. I mean, neither is ESS, which means it's not an ESS. So this is not an ESS for all values anyway. This is not an ESS under this condition. Is that clear to everyone? Yeah, neither of those two are stable. Now what will happen? The one possibility is, do you think that if you start with all Hawks, will everybody turn into Dow? No, right? They will, because that can't happen either, that we have shown, right? Because that's also an unstable strategy. So they will stop somewhere in between. And how do we find that? To find that basically, we basically find general condition under which, remember what this means, this is the average payoff of Hawks, average payoff of Dow for an arbitrary value of proportion of Hawks or Dows. Okay. So remember if you go back to your notes, we wrote down expressions for this and this. Okay. And in fact, we even solved this equality. And then if you solve the equality, what will you get? So I won't redo all the steps now because you have done that we have done that in the morning. So go back to your notes and we wrote down the expressions for VH and VD for arbitrary values. We were not assuming one of them is rare or dominant in that case. For any arbitrary value of P, where P is the proportion of Hawks, we wrote down this, we had expressions, and if you set them equal, you will find that P is equal to C, and the mixed strategy will be now stable. You can conclude that the mixed strategy is stable only when the pure strategies are unstable. Whether mixed strategy is stable or not. Well, you have to go back to the previous linear stability analysis. You have to plot the entire function f. This question is, there are multiple pure mixed strategies. Which of them is stable? Then in those cases, the only way really is, plot the entire function f as a function of p and identify all the equilibrium, and then the extremes should correspond to pure strategies, all the intermediate will be mixed strategies, and then identify each of them, whether it is stable or not. It's a good question. Yeah. Of course, this is easy when there are only one intermediate mixed strategies. Is that fine? Okay. So now I will give you a short problem to do, which is an extension of this Hawks and Dows. Imagine that in addition to Hawks and Dows, you also have some clever individuals. They have. One very peculiar property of this Hawks and Dows were, when a hawk interacts with hawk, they were hawks. When a dove interacts with dove, they were always doves. Doves were always doves, hawks were always hawks, right? Can you think of a cleverer strategy here? Because imagine if both of them are hawks, they get V minus C by 2. But imagine that if I make an initial peace-loving move, then maybe I should reciprocate that, okay? And in that case, both of us benefit because neither of us will then pay a cost of C on an average. So it's good to be a hawk only when the other person is always a dove, okay? Only when I'm convinced the other person is a dove. If the other person can negotiate, maybe I should also be like that, okay? So let's think of a new strategy called, what should we call it? Reciprocator, maybe? So what this reciprocator will do is, if this person encounters, a rigid, let's call there are 3 strategies now: a rigid hawk, a rigid dove, and this guy, okay? So in this now, if he encounters a rigid hawk, this guy will become hawk, okay? If this guy encounters a rigid dove, and if this guy encounters another of that fellow's own type, what do you think that person should do? They should both be. That's one possibility. It's up to you how exactly you want to model that situation. They could both become dove, or they could become hawk with some other probability, because they have no idea who that person is, right? Okay, so that's something you can play around with. So imagine you have these 3 strategies, this rigid hawk and rigid dove. Can you now write down a payoff matrix for these 3 strategies and then identify the ESS? So strategy is say, first you have to write down the payoff matrices. Once you have done the payoff matrices, find all the pure strategies, and then for each pure strategy do an invasion and see whether the invaders are better off. Okay, and then with that we will end this, I think, my last class here. Yeah. Yes. Oh yeah, that's a good point. So yeah, what should you do if you are rigid dove? I'm sorry, I didn't think of it. If I do meet a dove, what should I do? I should become a hawk because I will have a full resource. Okay, yeah, that's a great idea. Okay. Cool. Nice. Sorry? You had a... Oh, this one you mean? As in, if I'm meeting a hawk, should I become a dove? Then I will get 0, right? But if I do have... It depends actually V and C's. So write down the payoff matrix and then identify ESS. How much time do you have? What's the time now? 2:10. I have half an hour now. I have plenty of time to figure this out.